So this is the video on the calculations of the iodine clock reaction. And we're going to find the activation energy, and then we're going to use that to determine the calculated rate of the water bath temperature. But I'm not going to do that part. I'm going to head you in the right direction, just like I did before. I'm going to give you a pretty good start on the calculations here. So here are my times in seconds. All your times should be in seconds. If you have them in minutes and seconds, make sure you convert those. And these numbers that I have are not going to be the same as yours, though the temperatures are. The temperatures are correct, though we'll have to change them to Kelvin. So make sure that you follow along with your data, and you should be fine as far as the calculations. Okay. Now we need to find the rates for each temperature, and the rate is going to be equal to the initial concentration of the thiosulfate when we begin the reaction. So we have to show the dilution, but the final concentration of the thiosulfate ion is 0. So we want what do we start with? What do we initially have? And since it's the same for each reaction, we only have to do this once, and this is the answer. This is 1 × 10⁻²⁴ molar. So we take the stock solution, there's 5 mils of it, and it gets diluted to 30 mils by adding on in the other solutions. So that's our initial concentration of the thiosulfate. So our rates, and I'm just going to do the 2 of them. You should do all 3. You have to do for the water bath one as well. But we have the concentration that we start with for the thiosulfate ion. So that's the same here and here. And then we divide by our times. And these are the rates that I got for the room temperature and the ice bath. Okay, so to work with our Arrhenius equation, we have the natural log of the ratio of rate constants is equal to the activation energy over the gas constant. And then we have T1 over T1 minus 1 over T2. Well, I show in our lab book that the ratio of rate constants is equal to the ratio of rates. So I won't show that here. That's in the lab write-up. But because of that, we can use the rates we just found to determine EA. So I'm taking rate 2 to be equal to the rate at room temperature, and rate 1 to be equal to the rate at the ice bath temperature. And I put in the values we just found. 8.31 joules per kmol is the constant, the gas constant that we'll use. 1 over 276 and 1 over 295. Those are our temperatures, the room temperature and ice bath temperature. Now, when we solve this, we have the natural log. Take this number divided by this number, and we end up with 2.493. Units are canceled. We have EA over 8.31 joules per mole. These K's will cancel. And then we have 1 over 276 minus 1 over 295. And this becomes 0.913 over here. EA 8.31. And then we can just do it step by step. This will be 0.003623. And then this reduces to 2.33 times 10⁻⁴. So I'm just doing all of this in my head really quickly. No, I have it written down here, but it's really messy. So I figured I'll just write it out. Sometimes it's easier to see what's going on when someone does it slowly like this. So we have 0.913, and then I'm going to take this number divided by this number, because this goes here. So it's this number divided by this one, and it gives the EA times this divided by this gives us 2.804 times 10⁻⁵. So EA is going to be 0.913 divided by 2.804, just keeping an extra digit there so we don't lose too much. We have accuracy. And we get this number. It's going to be a large number. It's going to be in the tens of thousands or hundreds of thousands, because we're for EAs, that's what they usually are. And we can reduce this to around to this. And you're certainly free to change this to, kilojoules per mole. But right now we're going to leave this, because now that we know EA, should report EA in kilojoules per mole. So it'd be 30, in this case, it'd be 32.6 kilojoules per mole. But we're going to need it in this form, because we're going, once you have that, you're going to determine the rate for the water bath. And so we're going to use the information. This will be room temperature. So this is room temperature. But now we're going to replace this T1 with the water bath temperature in kelvins. So we've just determined EA. We know this. You have these values, and you can solve for your rate. But I'm going to stop here, because these numbers will be the same. This will be different, and I think this one will be different as well. This will be the same. And then you just solve for the rate. Then it wants the percent difference, but I think the equation that I give is pretty straightforward. If you have any questions, of course, you can email me. But that's the basic idea for the calculations.